So, welcome everyone. Today, we're going to use this time. I should have a quick look at the agenda. I'm assuming there's nothing extra on there. Today, we're going to use at least majority of this time to let Skarbek run through on his KubeCon talk. So we'll do this as a full run through with questions at the end. And this is as much kind of for everybody here to also learn about the topic of the talk, as well as us provide any feedback to the talk itself. So hopefully this gives a bit of a kind of like real life type of rehearsal for Skarbek before KubeCon next week. What I'll do, Skarbek, is record this. If you want this beforehand, then let me know. Otherwise, after you've done your talk next week, I'll publish it up and we can actually like put it as with your talk title in case people want the topic as well. So with that, I'll hand over to lovely John Skarbek, who is going to teach us all about multi-clusters. So welcome Skarbek, over to you.
Thank you, Amy. Good morning, everyone. As you know, my name is John Skarbek, and today I'm going to have a discussion with all of you regarding how GitLabcom has reduced the cloud bill by deploying additional clusters, Kubernetes clusters. So I am John. Feel free to just call me Skarbek. I'm a beekeeper, but I'm also a site reliability engineer for the delivery team at GitLab. Been here for about 3 years. Been creating all kinds of fun incidents, and everyone loves me for it. In today's conversation, I'm going to start a little bit with how GitLabcom got started with Kubernetes. I will discuss one of the problems specific to cloud costs and the use of highly redundant clusters that we came across. I will then highlight the solution that we chose to alleviate that problem, and then go over some of the bonus wins that we are able to achieve with said solution. So firstly, what is GitLab.com? We are the SaaS variety of the GitLab product, a full-blown DevOps platform built into one application. GitLab itself is a giant Ruby on Rails monolithic application. It does have some bits of Golang sprinkled in here in a few places, but for the most part, Ruby on Rails is the primary driving part of the application. In order to make GitLab.com easier to manage as we've scaled our SaaS application, as well as just the growth over the course of time, our infrastructure team has had to break up chunks of the application into different components. This has enabled the infrastructure team to better manage and control the infrastructure and ensure we have decent observability such that we can manage it in a very easy fashion. Likewise, a few years ago, we started the process of creating a Helm chart such that end users who utilize GitLab can deploy the entire GitLab application inside of a Kubernetes cluster. So now that time has passed, we have had to make changes to our application such that it is now a cloud native application and does appropriately work inside of Kubernetes. With all those pieces now put together, in 2019, our infrastructure team started to look into what it will take to get Kubernetes in place and start migrating parts of our infrastructure into Kubernetes. And at this point, we now have a hybrid architecture. We've been running in Kubernetes for a little bit now, and about 90% of our front-end workloads are now deployed into Kubernetes. Much of our stateful applications or stateful components, such as our databases and file servers, they remain as virtual machines. All of that managed via Chef and Terraform at the moment. So back when we got started with Kubernetes, we did not want to use our existing tooling to figure out, learn, build, and manage, upgrade our Kubernetes clusters. So because of that, we wanted to choose something that was going to be very quick and allow us to, in a very simple manner, configure a Kubernetes cluster available to us. So we do utilize Google's cloud platform as our infrastructure provider, So it was very natural for us to check out the Google Kubernetes engine, or GKE. And doing so, this allowed our infrastructure teams to focus on what we deem more important to us. Um, that included things like ensuring that we could run Kubernetes alongside of our virtual machine infrastructure. And because that we knew migrating into Kubernetes was not going to be a short process, this is a multi-year project for us. We needed to ensure that we had the compatibility between an application moving from a virtual machine into Kubernetes and go back and forth in case we ran into problems and needed to roll back during the migration period. So we wanted to make sure that our observability was in place and was backward compatible with whatever infrastructure and application was running on. We wanted to make sure that our deployment mechanism worked. That way, when we deploy to our virtual machines, we could also deploy the application to Kubernetes without impacting the delivery team unnecessarily. So with this, we chose to utilize GKE, and with that, we followed Google's best practices for setting up Kubernetes clusters. We wanted the best redundancy possible, so we made a regional cluster and we ran with it. This enabled us to migrate our very first application. We chose to migrate the GitLab container registry feature of the application. This is a very relatively small, lightweight Golang application. It doesn't have a lot of heavy dependencies in our downward application stack. It doesn't move a lot of data, but it does see a lot of traffic. It's a very heavily used application. So it was a perfect stateless application for us to get started and learn some things with migrating applications. So we were able to, again, make sure all of our observability was working as we desired, making sure and fixing any bugs that we introduced for our deployment mechanisms. Um, and we could test and validate that changes that we make to our virtual machine infrastructure land inside of our Kubernetes infrastructure as well. And this was very important for us because we wanted to be able to set the expectation for how we run Kubernetes and determine what we need to look forward to when it came to future migrations. We wanted to make sure that we thought about all the possible scenarios and understand what our workloads and how they are going to behave when they're running inside of a Kubernetes infrastructure, because it is very different than running inside of a single virtual machine. And one of the things that we targeted was what a regional cluster was going to have an impact for regarding cloud costs. And that's kind of the pain point I want to talk about in my in this talk. So here is a diagram that is showcasing the basic view of what network traffic is going to look like inside of a regional cluster, from the front door all the way down to a web service pod. So inside of a regional cluster, where you have nodes that span across all zones, a deployment technically consists of two primary things: the deployment of the web service itself that's going to run the application, or in our case, some component of GitLab. And you have the Nginx ingress controller, or a configuration for an existing ingress controller. We utilize Nginx ingress in our particular case. So again, because we use Google's cloud platform, we are also provided with a single ingress endpoint, or internal load balancer, provided to us inside of the Google network stack. So doing so provides us with a very special, happy path and a potential bad path where traffic can take that will change the behavior of how an application works. And this is kind of important for us to understand what that might look like. So when a client request comes in through our front door, in this case, we use HA proxy, and that traffic gets filtered into our regional cluster, we're going to land on an Nginx ingress controller. The only purpose that the ingress controllers do here is a little bit of buffering and then some load balancing. With the way that a regional cluster is configured, in the way that an ingress controller learns about its environment so it understands where to load balance traffic to, there's the possibility that that traffic might get load balance into a pod that exists inside of a different zone. So the happy path would be that not happening. An ingress controller inside a zone B takes that client request and proxies it to ideally the same node, but the best solution for us would be the same, or a pod that exists in that same zone. In cases like this, we do not incur any additional network latency because we stayed inside that zone, so there's no additional network hopping. And because no traffic has egressed from that zone, we have not hit a new charge that gets added to your cloud bill. The worst path would be when an ingress controller does need to cross a zonal boundary. Again, because he's got knowledge of all web service pods and he's just going to choose one, not at random, he's got some sort of algorithm, but if he chooses a pod that lives in a different zone, you're going to incur, albeit minor, a network latency because we're adding additional network hops to get to that node. And because we are egressing traffic from that zone, you're going to incur a charge, a network cost for the bandwidth that gets utilized for that connection. So let's look at how bad that could potentially be as far as costs go. So prior to us moving our next large service, we did a quick investigation. Now, keep in mind, all cloud providers do this. So insert your favorite cloud provider calculator and network pricing schema here. But for Google, in our particular case, if you're moving about 500 terabytes of data across a zone, that's going to charge you a little over $5,000 over the course of an entire month. That's not something to blink an eye at. That's actually quite expensive. So we need to think about those costs in terms of all of GitLab to determine if that's the cost that we're willing to accept or if it's something that we should solve for. So if we look at all the web services GitLab has, we're moving petabytes of data over the course of an entire month. That's quite a bit of data. And if we are serving all of this in a region that has 3 zones, about 2/3 of that traffic is subject to crossing a zonal boundary. That is, tenfold more expensive than our estimation. So like, this is a problem we're solving, but this also gets into one of the problems related to cloud costs and, predicting what your cloud bill is going to look like. Again, we used a managed cluster. Google tells you precisely how much they're going to charge for that cluster for a given hour. We know the instances because we choose which instances we want to run inside of our clusters. So we could predict how many nodes we need to run to serve our workloads. And we could go to our financial person and say, hey, it's going to cost us this amount to run this cluster. What's harder to predict, especially for GitLabcom, because our network traffic is very much driven by a customer base and the workloads that they have and the amount of data that they store on us, it's harder to predict how much it's going to cost us for the network bandwidth that gets utilized. And especially if it's a cross-zonal boundary item that we can't necessarily control. So one thing to keep in mind in regards to predicting network costs is that you're not going to be able to prevent those zonal boundary crossings happening everywhere within our stack. So here's just a diagram showcasing what happens below a web service pod, where eventually, due to the way that we have deployed our infrastructure, there is the possibility of crossing a zonal boundary. Eventually we'll have to talk to a file server or a database server. And this is a cost that we have to accept at that point because it's the way that we've deployed all of our servers across an entire region for the ultimate redundancy. However, if we could solve for how our front end layer and how the Nginx controllers are load balancing traffic, we have improved our situation to some extent. So, as the title of my talk suggests, we decided to deploy one cluster for every zone inside of a region. So now if we look at the network stack specifically, like this chart showcases, when your traffic goes through an HA proxy node located in, say, zone B, it's going to favor sending that traffic to a cluster located in that same zone. That means that client request is going to get handled by an Nginx ingress controller located in zone B. And therefore, because of the way that these clusters are configured, that controller does not have any knowledge of any web service pod in any other zone or any other cluster. Therefore, that request can only go to a web service pod located on a node somewhere inside of zone B. So we've eliminated the cross-zonal traffic happening in our front-end layer, and we've eliminated because of that, we've eliminated the network costs associated with that bandwidth. And we've also eliminated the network latency that might get incurred as we potentially would have been crossing zonal boundaries. Again, however, below web service pod, we will still incur the zonal bandwidth charges that happen as we talk to file servers or database servers. But again, that's an unavoidable cost that we've learned to accept at this point. So there's a few benefits that we gain from having all these additional clusters. One, it's a lot less expensive. We use a managed cluster. It costs us a few $100s per month to maintain these extra clusters in comparison to the tens of thousands of dollars it would have cost to manage the network traffic for just a single web service being pushed into a regional cluster, for example. We also get the benefit of being able to spread out cluster upgrades. This enables us to make sure that a cluster upgrade works properly and the cluster is healthy before we enable cluster upgrades on the additional clusters. We've got all this automated in a fancy way. This was also a very boring solution to us. Keep in mind that when we evaluated this, we didn't have very much stuff in Kubernetes. We had the container registry running, which didn't serve a lot of bandwidth, but served plenty of requests. We might have had a few backend Sidekick services inside of Kubernetes, but those aren't subject to the same front-end workloads that our web service pods are. And lastly, this was a recommendation by Google, so we took advantage of that. For the ultimate redundancy, however, HA Proxy is aware of all of our clusters. That way, if we do suffer some sort of failure inside of a cluster, we could isolate it, and that traffic will get load balanced to our two other clusters automatically. So what options might be available to everyone if multiple clusters is not a viable solution for you? One of them is going to be a service mesh, which I'm sure many of you are probably thinking about. And so there's many to choose from. And at the time that we were evaluating what we wanted to accomplish, we don't have a service mesh installed anywhere inside of the GitLab application. Again, we're using our Helm chart, which also does not have any sort of service mesh. So we have all the puzzle pieces that bring our applications together from the get-go. There's no need to add this new service. If we had to do that, that would have required us to determine which service mesh we wanted to go down, learn that service mesh, and figure out how to configure it, observe it, monitor it, etc. And this just didn't seem like a viable option. Another option we could have gone down was modifying how we deployed and operated our first regional cluster that we had created. However, the benefits of using more than one cluster, we saw very quickly and decided to use that over regional cluster. But you've got options to the way that you make changes to how you deploy your node pools, which would require either additional deployment and service objects or modifications to existing deployment and service objects. And the last potential option that I know about is there's a Kubernetes alpha feature called topology aware hints. This is still an alpha feature, so even we at GitLab can't yet take advantage of this, but there's now more stuff available today than there was when we were first looking into this problem. So is this more complex? I think we could argue both directions on the complex nature of having additional clusters in your infrastructure. It is more complex in the fact that you do have more things to manage. But in terms of, say, where your workloads are running and how many nodes are going to be running, the amount of traffic coming into each of our zones would have been the same if we were running a regional cluster. So the amount of nodes that are running to service our workloads isn't necessarily more. We just have nodes designated to specific clusters now instead of the same amount of nodes being designated to a single cluster. And at this point, we're taking cluster configurations and we're kind of copying and pasting them. We're just stamping out new clusters as necessary. The amount of difference between our clusters is very minimal. Which zone it's deployed into, the network space it gets utilized, and maybe the name would change, but it's effectively the same. The deployments or the workloads running on these clusters is pretty much identical. They all serve the same purpose. They serve our front end traffic. So you have both the configurations for the clusters and the configurations for our deployments are pretty much identical. So they're very well defined and easily manageable at this point. We're treating our clusters more like cattle versus pet clusters. And in our case, the observability, there isn't very much of an observability overhead. I think we spent more time trying to figure out how we wanted to label these clusters than anything else. And we just needed to expose how we wanted those clusters to look and like the location rather. So some bonus items. Now that we've got multiple clusters, we have fun ways to mitigate incidents. So this is a chart that is showcasing the fact that we ran up against a limit in our NAT port usage. When we first created all of these additional clusters, and then over the course of time, as we started pushing more things into our Kubernetes clusters, we ran into a situation where when we did a deployment, all of our nodes in Kubernetes were pulling the new image that we wanted it to run. This created a little bit of network havoc. So to mitigate this, we simply told our deployment mechanism to don't deploy to all clusters at the exact same time. Instead, deploy sequentially. So doing this enabled us to mitigate the issue, and then our infrastructure team could go back and figure out what they need to do or make whatever changes necessary for our NAT device. And then later on, we could revert that change and deploy to as many clusters that we wanted to. One of the more important items I want to highlight is the ability for us to tune specific workloads. So here is a chart showing how many pods are being run across all for the API workload. Here's the pod count for all of the clusters. So we could see right in the middle of the chart, we deployed some sort of change that lowered the amount of pods the API service needed to run. So this enables us to compare the behavior of how either Kubernetes or the workloads are behaving on a per cluster basis. And we can make whatever changes we want here. And we have the ability to compare this test change in one cluster to our existing two control clusters per se. And if we see a positive change in behavior, we can push that change out to all of our clusters. If we see negative behavior, we would obviously roll that back. Or if it's incident inducing, we could isolate that cluster temporarily and push the fix through. But this enables us to make whatever change we want. We could change how we deploy that workload. We can make changes to how those pods request information out of the nodes, like the resource requests and resource limits. And we could also change the horizontal pod autoscaler. So we could change the metric that we scale on and also the target metric value that we utilize for determining when it scales. And we could also make changes to the application itself. We could change how many Ruby threads we want. We could change the memory usage of a given Ruby thread, etc. Like the sky is nearly the limit in this particular case. And the last item I want to highlight is the ability to introduce fun maintenance procedures when required. So here's a chart showing web requests over the course of time across 3 clusters during a maintenance procedure event. So in this case, we're fixing a bug on our Helm chart. The fix for our Helm chart would have been incident inducing if we did not roll this out in a very controlled manner. So what we can do now is remove all the traffic coming into a single cluster if we wanted. All that additional load would get sent to our existing clusters temporarily. We could then push the fix to the cluster that's inside of a maintenance mode. After the fix is pushed in place, we could then send customer traffic back to it and repeat as necessary. So to wrap up the conversation, look at your cloud bill. determine if this is a problem that you might be suffering from. For us, we knew this was going to be a problem, so we were predicting the future effectively before we migrated our next big service that took a lot of client workloads. Also, keep in mind what solutions are available. There's more solutions available today than there was when we were first looking at this. And also keep in mind that we were still relatively young with our adoption of Kubernetes. So we didn't really have a lot of workloads that depended on it. And it was easier for us to create additional clusters versus exploring a different solution. That might be wildly different today than it would if we started solving this problem today versus a year ago. And also consider where this problem might lie. For us, it was very Kubernetes specific. But for many people, it may be somewhere else inside their entire tech stack, and it might be worth checking out where that bandwidth is being, or where that cloud charge is coming from to determine whether or not it's a problem that you need to solve, or whether or not it's a problem that may exist somewhere else. So thank you all for listening to me blabber on for quite a long time. At this point, I'll take questions.
Thank you. Does anyone have a question? So I have one around, so you mentioned that when we made this decision, it was like some time ago and things have changed. There's other options and things like that. So if we were facing this problem now, how do you think we would have decided if like multi-clusters was still the way forwards?
I don't know the answer to that question. I've thought about this. If I had to guess, we would have probably gone down a similar route, or we would have made changes to the way that we deploy. So it's been easy for us to stamp out multiple identical configurations for everything. And I think if we were to want to see the benefits of having the ability to test multiple clusters, and we saw that as our primary benefit, I think we would still go down the same route. I think our other option that we probably would have checked out a little bit more was trying to figure out what we could do with an existing cluster and maybe just make changes to the way that we run our workload such that we could still figure out ways to keep that traffic inside of a single zone. So I don't know, that would require a little bit more research now that we've got a lot more stuff inside of Kubernetes these days.
And then on calculating costs, so as someone who wants to go away and do this, with calculating costs, how much did you factor in the sort of potential growth and like the kind of increasing cost in terms of trying to decide when to do this now? Like, have you got any tips for how to actually decide when to make this change?
That's a good question. That's a really good question.
I suppose a simpler one then, like, how much did we have to do that when we made this decision? Like, did we just take a kind of here's our bill right now and kind of assume it's going to increase in the future, or did we try and do any projections on like scale as well?
So I know that when we were looking at this, we were only looking at this for the perspective of the application that was next to be migrated. We weren't looking deep dark into the future, taking into account all of our services, which I think is a fine method of determining your initial like start point. I do think you need to take into account all of your web services in order to get a good overview as to what that cloud bill is going to look like in the future. And I guess if you know how quickly you're growing, you might decide whether or not you want to take growth into account. I think for us, because we knew one service itself was going to be expensive enough, we knew it was worth looking into and solving that problem pretty much immediately without having to look at the future. Just looking at one service was enough to say, hey, this is going to be problematic. We should solve this problem.
I see. Okay, yeah, that makes sense then. So us kind of having that prior knowledge of our services and how they're kind of different traffic based was kind of key for this. And then cool. I feel like I had one more question. Oh yeah, so we have three, well, we have 4 clusters, but in the sake of this talk, we have 3 clusters. Is that the right number? Like what would be the kind of decision making to have 5 clusters, for example? Like how do we pick the number of clusters?
I don't think there's a magic number of clusters. I think it's primarily based on what traffic is doing and what kind of workloads you need to be running. You know, we've effectively created like a front end layer of clusters that handle, you know, a set of clusters that hand front end traffic. And then we've got a single cluster that handles all the back end work. And so far that has worked well for us. You know, we haven't had any problems with the Kubernetes API blowing up because we've got too many operations handling. And I think that might be one of the governing factors is how you've configured those clusters. Do you have enough network capacity, for example? And then for clusters that span a lot of nodes, it might be what limits are you running into within the Kubernetes API itself? You know, even though GitLabcom is a massive application, we aren't yet hitting the limits of Kubernetes itself. We're closer to running out of the available IP address space just due to the way that we configure things. So we'll probably run out of that before we run out of. Can you guys see? Okay.
Before you run out of cats.
Yeah. So no, I don't think there's a magic number to determine how many clusters that can be run. I think as long as you're observing the Kubernetes API and its performance to make sure you're not unnecessarily bringing Kubernetes down, as well as not running into limitations, whether that be your cloud quota limits or maybe the Kubernetes limits for Kubernetes itself, because I know there are some limitations within Kubernetes API that may prevent you from doing certain things. One prime example is a single node can't handle more than 110 pods, for example. We're nowhere near that limit, but you know, stuff like that, one should keep in mind when it comes to evaluating maybe how many clusters to run.
There's one thing, this is not relevant to your topic at all, but you've made me think about it, right? Which is that as we, in the future, like clusters could be an interesting breakpoint in the deployment process. So like as a phased rollout per cluster. And I wonder at that stage whether there's actual benefit to us having more smaller clusters that give us a bit more of a granular deployment flow versus there's obviously the overhead of like running more clusters, right?
So I've thought about that. And I really think what runs on Kubernetes is going to really drive the direction for that. And I say that because we are more subject to how long it takes for things to deploy. You know, it takes an excruciatingly long period of time for our Git deployment to complete because it takes us like 260 seconds before a pod will end. And like we run nearly 100 pods across all of our clusters for that deployment. Like that's a little, that deployment itself takes an excruciating long period of time to complete. I think if our deployments were like super speedy, then that entire model would change and we may decide to do something different. But I really feel like that it's more workload driven because we're not running into any fun limits within Kubernetes at this point. And like we're scaling very well. Like we may bring on a lot of nodes in order to perform and deploy, but since we fixed that one Helm bug issue, I'm hoping that happens a lot less. But I'm also hoping that we're not stressing Kubernetes in my mind.
Mm-hmm. Mm.
Do we pay for master nodes or only for the node pool?
Kubernetes, or Google rather, charges an hourly rate for having a single managed cluster. So you pay, I think for the course of a month, it's like $75 per cluster, if I recall correctly. And then you pay for every single node that you run. So we don't pay for the API nodes that run Kubernetes. We just pay a service charge for the cluster plus the nodes that run that cluster.
Yeah, I was thinking about if we are in a special position compared to others that so usually people runs Kubernetes on cloud, so probably the billing will be similar. But if you are going to run Kubernetes at home, let's say on premise, and then you have to make the API server highly available, which means at least 3 nodes. You need 3 master nodes, 3 etcd nodes. It really depends on how you want to make it highly available, right? So let's say at least 3 extra nodes. Going the route multi-cluster is kind of really expensive, because then every master node, every cluster needs highly available master nodes, highly available etcd and things like that. So that's why I was asking, because if we are paying, say, pennies for having the extra cluster, because in the end the number of nodes will be the same, right? As you were mentioning,
effectively,
we're just splitting the workload over several clusters. But so that's probably a good point to make, that if you're running on a cloud provider that just the bill is similar, let's say, then you can go this route. Or if not, you can do some of those things using multiple deployments instead of multiple clusters.
I am curious as to how other cloud companies charge for that, because it doesn't matter. Like, we deployed zonal clusters, so you get one API node for our zonal clusters, whereas our regional cluster, you get one API node for every zone you deploy to. Which, the regional clusters are more redundant in terms of the Kubernetes API. Our zonal clusters are less so. So anytime there's maintenance being or occurring under zonal clusters, it kind of puts everything on pause. And luckily that happens during APEC. So it's only Craig and Graham who sees that problem, luckily for us. But the cluster, like the charge for running that cluster is the same between the zonal and the original clusters, at least for Google. But I'm curious as to how other cloud providers choose to bill for that kind of thing. Because Google has changed their pricing model ever since they've introduced it a few times. So that might be worth mentioning. I would have to figure out what other cloud providers do to see if I can't make any beneficial mention about that.
You could probably ask them, like, just generally, if you get a question on those lines, because you'll probably have people in the audience who could answer on, who like could comment on that.
Yeah, that's a good point too.
Awesome. Well done, Skyback. That's a good talk.
Cool. Any additional feedback for me?
I
have one thing which I just thought during the talk. By the way, awesome talk. Really liked it. And what I told you, I think last time already, I think I saw more clearly now what you could do with adding some pictures maybe to the slides. Because I think
I added one set of emojis.
Yeah, I think you are telling a story, which is really nice. And I think it would be cool at places like at the beginning when you say, first we were at, with GitLab with VMs, then we wanted to switch over to Kubernetes. Like there's a lot of room on your slides, besides the text, to just have something showing a very simple diagram with first our maybe VM deployment structure, and then when you go to the next slide, you can see maybe something like an arrow and showing, okay, now we are going to VM, how it looks like. Because I think if you get a visual representation of what somebody is talking about, then it's easier to memorize and get a picture of that. I mean, I wouldn't add too much, but I think this kind of storytelling in pictures would give it something, and then it would fill empty places on the slides. But I'm personally not very great at doing pictures and slides, so I have to admit.
I don't disagree. I'll have to figure out, because it is kind of late to be changing slides, how to figure out if that's possible or not. But
Okay.
I'll check it
Yeah.
out. We'll see what we can do.
Besides that, I'm anyway a fan of not having too much on slides, so
Yeah.
I wouldn't put too many things on it. Just as an idea for storytelling. But yeah.
Yeah, I was going to make a similar suggestion. I was thinking, especially in a specific moment in your slides when you show the multi-cluster architecture, and then before going to, I think the slide after that is the one about other alternatives, if I remember correctly. So you just show multi-cluster architecture, you talk a lot on that, then you talk about service mesh, other stuff, and then you move on, right? So right before, so yeah, thank you, Scarbeck. So not this one. Let me, yeah, no.
So this was the multi-cluster. And this was just one where I'm like, hey,
Okay.
what's the complexity nature of having additional clusters?
No, it's not. No, I think 2 slides before, slide 12, I think. Is that correct? Yes. Okay. So you spent a lot of time on this slide, and there is before moving to the next one, when you start talking about alternatives that may be viable for others, you mentioned 3, 4, I don't remember, key benefits from this. So I think they are kind of, if these are points that are important that you want to make, they probably deserve its own slide with nothing else other than the text and an image. Okay, you can just put a big image, full screen, and the key point, the point you want to make, right? Because people looking at this slide is very dense. It serves you because you have to explain what we did. It gives you, when you start talking about this thing, is amazing, this slide, because it gives you, okay, we were going crisscross across all the zone, and this is what we are doing now. Fine, perfect. This is really understandable. But then you kind of change topic, because after you explain this, you're moving into, and we were able to do X, Y, and Z, which have no, there's nothing in the slide pointing me in the audience to that. And also there's also, let's call this, people tend to say fell asleep during the presentation, not that they really fell asleep, but basically you say, I'll just watch the slides. So you're just blurbing. Yeah. When you change, it's kind of a refreshing moment, right? So what's happening now, right? So the people have this, what's happening now. And usually help, I mean, again, if you don't have time to change the slide, just, that doesn't matter. But when you're making, instead of making a list in a slide, it's better to have 3 slides in a row, each one with 1 point. And only that point, right? Because it gives you context and help you guiding the audience through the point that you are making.
Yeah. Okay. I'll see what I can do with that. Might be able to do something. Cool.
Awesome. Well done, Scarbeck. Good luck with the talk. We won't speak to you before. And,
thank you much.
I look forward to hearing how it went.
Excellent. Well, thanks for listening to me. Thanks for the feedback. And if I don't see you all until I get back, I guess I'll see you most in half of October has passed. And Alessio, I might not see you until November, probably.
Who knows? I mean, it really depends on when we deliver. If it happens when you are in PTO, probably I'll be back when you'll be back as well. So we will see. We will see. It could happen at any time.
Yep. Alrighty.
Awesome.
Enjoy your vacation.
Yes,
thank you.
definitely. All right. Take care, everyone.
Attempt to. Bye, everyone.